Welcome back, everyone. This is Dr. Gallenstein, and we are back for lecture number 8. Now, today what we're going to do is introduce the topic of binary dependent variable models. So far in the class, we have looked at regression models that use continuous variables as dependent variables. Now, by continuous variables, I mean numbers that can take any value, theoretically negative infinity to infinity. But now what we're going to do is we're going to switch to models where our dependent variable is binary, typically a 1 or a 0. And we're going to look at two different models or two different approaches to doing regression analysis where our dependent variable is a binary variable. So with that introduction, let's begin. Okay, so a binary dependent variable. First, let's just review what a binary variable is. So a binary variable can take two values, and in our work, practically speaking, this is always going to be 1 or 0. So a binary variable, so when I say binary variable, that means it takes two values. But in practice, when we have binary variables, they take 1 or 0. Okay. All right. 1 indicates that the observation belongs to a particular group or characteristic. Sometimes this is called success. So it equals 1 if there's a success, or it equals 0 if there's a failure. But typically our binary dependent or our binary variables will indicate that it in an individual or group, whatever our observation is, belongs to a particular group or it has a particular characteristic. All right, and 0 indicates that the observation does not belong to that group or does not have that particular characteristic. So for example, and we're going to use this later, so for example, let's imagine a binary variable that indicates whether or not someone has a high school degree. So we're going to call it HS for high school. HS stands for high school, and this is going to be a variable that indicates whether or not someone has a high school degree. It equals 1 if they have a high school degree, and it equals 0 if they do not have a high school degree. All right, so that is a binary variable. It equals 1 if they belong to the group. It equals 0 if they don't. So it equals 1 if they have a degree. It equals 0 if they don't have a degree. It's binary. There's only two options. Usually when we name a binary variable, we name it by whatever the 1 would indicate. So if 1 is supposed to indicate that they have a high school degree, then we give it a name like high school or high school degree. And then it's kind of intuitive. If a variable is called high school degree, then I would immediately assume that 1 means that they have a high school degree and 0 means they don't have a high school degree. So we've used in the past a gender dummy variable, and we call it female. And it meant that it equaled 1 if they were female and 0 if they were male. So that's the kind of the logic. We give it the name that corresponds to whatever the 1 would be. Okay. All right, so here we go, binary variable, that's kind of review. All right, but now let's maybe go a little bit beyond that. The expected value, or the mean, the average, all right, the expected value of a binary variable is the probability within the sample that an individual will have a value of 1 for the binary variable. Okay, so let me just demonstrate this. All right, the expected value of our HS variable, so the expected value of our high school degree variable equals the probability, that's what the symbol, this P with parentheses, the probability. So the expected value of the high school degree variable equals the probability that the high school degree equals 1. Okay, so another way of putting that would be that the expected value of the high school degree gives us the probability that any individual in our sample has a high school degree. It's the probability within our sample that an individual has a high school degree, which means that the high school equals 1. So the expected value of high school degree variable, the average, the mean of the high school degree variable equals the probability of the high school degree variable equaling 1. All right, so the expected value is equal to the probability. Okay, so the expected value of the high school degree variable is the probability that an individual in our sample will have a high school degree. This notation, P parentheses, what that means is the probability that whatever is inside the parentheses is true. So the probability that the high school degree variable will equal 1, that's what this expression is. This is the probability, this expression, just notationally, the probability that the high school degree variable will equal 1. All right, so the expected value equals the probability. All right, so for example, the probability of having a high school degree in our sample or our example is the expected value of the high school variable defined in the previous slide. All right, so here's our high school degree variable. The probability of having a high school degree in the sample population from our example is the expected value of that high school degree variable. Okay. So the probability that high school will equal 1. All right. Okay, so now that's just a quick review conceptually. All right, now a binary dependent variable model. So a binary dependent variable model is where the dependent variable, right, where we normally have y, for example. So in the past we've always had income or wages or something, some continuous variable. But now what we're doing is we have a model where the dependent variable is a binary variable. So it's like our high school degree variable. So our high school degree can take two values, 1 or 0, and we're going to have that as our dependent variable. So we will regress the high school degree variable on our independent variables. All right, so this is a binary dependent variable model. It's a model that has a binary variable as the dependent variable. Okay. If we pause for a second and just kind of think conceptually, why would we ever want to have a binary variable as a dependent variable? Why would we ever want to know this? Well, actually, it's somewhat intuitive. We may very well want to know what factors influence whether or not an individual has a high school degree. We might want to know what are the factors that affect whether or not a student will graduate high school or not. It's a binary outcome. We want to know whether they graduate or they don't graduate. It's not a continuous outcome. It's a binary outcome. I want to know what are the factors that determine or influence whether or not an individual student will graduate from high school. That's a very important or relevant question because we want to make sure that students graduate from high school or graduate from college, So we want to know what are the factors that determine whether or not an individual will graduate from high school. And so if we wanted to know that, then we would use a binary dependent variable model where our dependent variable would be a binary variable like this HS variable where it equals 1 if they have a high school degree and 0 if they don't. I'm sure they can think of other examples. In fact, binary dependent variable models sometimes is even more common than models that have continuous dependent variables. These are very common to know whether or not someone graduates from high school, whether or not someone graduates from college, whether or not someone enrolls in college, whether or not someone applies for a microfinance loan, whether or not I'm trying to think of some more examples. I can probably sit here and try to think of examples all day. But the point is that we oftentimes want to know the determinants of some binary outcome. Whether, does someone have something or not? Does someone do something or not? Where it's one or the other. It's black and white. All right, we might want to know what are the determinants that determine whether or not someone, sends their kids to school, whether or not parents send their kids to school or not, school attendance, for example. Okay, so that's why we would use this, is we want to know what are the factors, what are the independent variables that will affect this binary decision or this binary outcome. We want to know what's beta 1. What is the effect of our independent variables on this binary outcome, whether or not someone has a high school degree or not. Okay. But now you might recognize that this introduces some potentially interesting challenges. So the first thing that we probably will notice is that the interpretation or the way that we would approach this model would be very different. So let's say we ran this regression. So now the dependent variable only takes two values. It's only 1 or 0. So the way that we would interpret this beta 1 would have to be very different. We need to realize that by looking at this is a very different model than we had before. Now, if you remember from when we had a continuous dependent variable, if we had a continuous dependent variable, and if we ran this regression using ordinary least squares, we would interpret beta 1 hat to be the change in the dependent variable given a unit change in the independent variable. We would say, how much does the dependent variable go up given a unit change in the independent variable? So let's just, for example, let's just say that instead of having a binary variable here, let's go back and we say we had income. All right, so we have some continuous variable here, just for illustration. Let's say that there's a continuous variable here. If there was, and we ran the regression, and we got beta 1 hat, we would interpret it as the change in the dependent variable, or the change in income, given a unit change, a 1 unit change in x1, in the independent variable. Okay, but now with a binary dependent variable model, it changes. There's no such thing as I can't say how much the dependent variable changes given a unit change in the independent variable. I can't say that because the dependent variable only takes two values. It can only be 1 or 0. So then how do we understand this model? How do we interpret a coefficient that comes from a binary dependent variable model? Okay, with that, I want to go and I want to talk about two different approaches to using binary dependent variable models, and I think that this will illustrate to you how we can understand these models and interpret the coefficients that come from them. Okay, so that kind of prefaces. Now let me introduce the first approach. The first approach is going to be called the linear probability model. Now let me go into that. All right, so this is the model we just had a moment ago. Now remember our conditional mean independence assumption. All right, so we know that the expected value of epsilon conditional on the independent variables is equal to 0. Okay, so here's our model. If we take the expected value of the model, what we get is this. All right, if we take the expected value conditional on x, what we get is this. We have the expected value of our dependent variable conditional on x equals just the linear equation without the error term, because the expected value of the error term conditional on x is equal to 0. Okay, so this is what we have. All right, so what we're doing is we're taking the expected value of our regression equation, and what we get is this. So what this is saying is that the expected value of the dependent variable is equal to just the linear function of the independent variables. All right, this should remind you of our population regression function that we did a couple lectures ago. Okay, so we have the expected value of the high school degree variable conditional on x equals this linear function. Now, remember that the expected value of the high school degree variable is equal to, it's the same thing as the probability. So let's remember that. So remember that the expected value of the high school degree variable, the expected value of a binary variable, is equal to the probability that that binary variable equals 1. So that means that this linear function of independent variables, so here we just have a simple linear function that has only one independent variable. We could have more independent variables. I'm just using this as an example. So we have a linear function of the independent variable, And that equals the probability that the high school degree variable will equal 1. So what we're saying, if the OLS assumptions hold, then the probability of having a high school degree, all right, the probability of having a high school degree is a linear function of the independent variable or variables. The probability of having, so what we're assuming is when we use the linear probability model, is we're assuming that the probability of having a high school degree, or the probability of that our dependent variable will equal 1, the probability is a linear function of the independent variables. Okay. So if we estimate a regression model using ordinary least squares and the dependent variable is a binary variable, we will have what we call a linear probability model. So let's go through that name, linear probability model. It's linear, means a linear function of the independent variables. It's a linear probability model. Why are we calling it a probability model? We're calling it a probability model because we're saying that this linear function determines the probability that the dependent variable will equal 1. All right, so this is a linear probability model. We're modeling the probability that the dependent variable will equal to 1. So we're modeling the probability that an individual will have a high school degree as a linear function of the independent variables in our model. So it's called a linear probability model because the probability that y equals 1 is a linear function of the independent variables. Okay, so then how do we interpret the coefficients using a linear probability model? How do we interpret beta 1 hat, for example? This is the most important. Now, so before, just by comparison, remember that if we had a continuous dependent variable, then beta 1 hat would be interpreted as the change in y given a change in x. All right, but now it's a little bit different. Now the dependent variable is binary. So now beta 1 hat is the change in probability that y will equal 1 given a 1 unit change in x1. So let me rephrase that. What beta 1 hat is, it's the change in the probability that someone will have y equals 1 or hs equals 1. It's the change in the probability of that someone will have a high school degree given a unit change in x. So if we can keep thinking about this, what I'm saying is, let's say that, so high school degree, let's say x1 is their grades. So as their grade goes up, beta 1 hat gives you the effect that an increase in your grades have on the probability that you will have a high school degree. So beta 1 hat is going to give you, it's a measurement of the effect of a change in the independent variable on the probability that someone will have a high school degree in this example. So if I run a linear probability model, that means I have a dependent variable, a binary dependent variable, and I use ordinary least squares. I just use the standard approach, ordinary least squares. I would get my coefficient, beta 1, and I would conclude, I would say, let's say the beta 1 was positive and significant. That would mean I would say that the probability that someone has a high school degree goes up by beta 1 hat given a 1 unit change in x1. Okay. Now, how do I interpret beta 0 hat? Beta 0 hat is the probability that y will equal 1, the probability that someone will have a high school degree, when all independent variables are equal to 0. So if the independent variable is equal to 0, beta 0 hat will give you the probability that the person will have a high school degree, or the probability that y will equal 1. So what is the probability that someone will have a high school degree if x1 equals 0? That's what beta 1 hat gives you. I'm sorry, beta 0 hat. Beta 0 hat gives you the probability that someone will have a high school degree if all the independent variables equal 0. So let's take our example of grades. So let's say x1 is the student's grades. It's their GPA in high school. All right. Let's say that their GPA was 0. They had a 0 GPA. And so beta 1 times 0 is just 0. And so if we want to know what is the probability that someone will have a high school degree when their grades, their GPA is 0, that will be beta 0. Beta 0 hat. Beta 0 hat will be an estimate of the probability that they have a high school degree when the independent variables are equal to 0. Okay. All right, when we're using a linear probability model, we will use the same goodness of fit measures and hypothesis testing techniques as with the standard ordinary least squares. So a linear probability model is where we just use standard ordinary least squares. We use the reg command in Stata. I'll show you in a minute. We just use a standard ordinary least squares approach to estimating the model, but the only difference is that we interpret the betas differently. We interpret the betas differently. Instead of beta 1 hat being a change in y given a change in x, instead beta 1 hat is a change in the probability given a change in x. A change in the probability that that someone will be in the group, the y equals 1 group. The change in the probability that someone is in the y equals 1 group given a unit change in x. All right, so the biggest difference here is that with a linear probability model, now we're changing the way that we interpret the coefficient. All right, I'll illustrate this in Stata, and we'll talk about it more. Now, the linear probability model has some disadvantages. So in a minute, I'm going to show you another approach to estimating a model that has a binary dependent variable. And then at the end of the lecture, I'm going to talk to you about how do we know when to use one model versus the other. When should I use a linear probability model versus the model I'm about to show you? Basically, both approaches have advantages and disadvantages. So first, I just want to summarize the disadvantages of the linear probability model as a way of motivating for why we would want to have another approach to estimating a binary dependent variable model. Okay, so the linear probability model has some disadvantages. One disadvantage is that the predicted probabilities, so basically y hat, if you estimate your regression and then you predict the outcome variable, the predicted values can be illogical. It can be greater than 1 or less than 0. All right, that's a disadvantage of this model. I'll make this more clear when we get into this data illustration. Another disadvantage is that the model is necessarily heteroscedastic. We know that the linear probability model will have heteroscedasticity. Now, we know from our last lecture, lecture 7, that heteroscedasticity, when we have it, we'll use the robust standard errors. So this isn't a major problem, but it's somewhat of a disadvantage. When we use the linear probability model, we know that we need to use robust standard errors because there will be heteroscedasticity. Okay. But now this problem is going to be our big problem with the linear probability model. That basically, if we were to predict values, if we were to generate predicted probabilities using our results from a linear probability model, those probabilities would be, they would have the potential to be greater than 1 or less than 0. And probabilities cannot be greater than 1 or less than 0. And so this creates just a logical problem that these results don't, these wouldn't make sense. And so if we needed a model that actually generates probabilities that are logical, that means probabilities between 0 and 1, then we would need to use a different approach. And so that would motivate using a different model, something different than the linear probability model, which we're going to get to now. This is on the Probit and Logit models. Probit models and Logit models are models that are used to study binary dependent variables. So if we want to study the effect of some independent variables on a binary dependent variable, two models that we can use are called the Logit and the Probit and the Logit model. And so I will now show you what these models are, and then we'll talk about their advantages and disadvantages. Okay, so Probit and Logit models are alternative approaches to estimating a regression with a binary dependent variable. These models generate predicted probabilities between 0 and 1. So that is a major advantage of these models. And so if we're estimating a model where we want to generate predicted probabilities, then we need to go with the Probit and Logit model because they're able to generate probabilities that are between 0 and 1. Let me illustrate. So above, I'll just go back to it. We said that with a linear probability model, what we're saying is that the probability that the dependent variable will equal 1 is equal to some linear function. It's some linear function of independent variables. All right, so the probability that the dependent variable will equal 1 is equal to some linear probability. Some linear function of the independent variables. For the Probit and Logit models, we're actually assuming something different. We are assuming that the probability that the dependent variable will equal 1 is equal to a non-linear function of the regression line. So we have the same regression line here, okay? But we're saying that the probability that a dependent variable equals 1 is equal to some nonlinear function of the regression line. So now it's not linear. It's not a straight line anymore. This g function, this g of something, this g function is a function such that g is always greater than 0 and less than 1. All right. When we do this, we're guaranteeing that the probability that the dependent variable equals 1, we're guaranteeing that the dependent variable equals we're guaranteeing that the probability is between 0 and 1, and that makes sense. You can't have more than a 100% probability that someone will have a high school degree. The probability that someone has a high school degree is going to be between 0 and 1. And so this structure, what we're doing here is we're saying we're using a function and saying that this function is always going to be between 0 and 1. That guarantees that the probability that someone has a high school degree, is always going to be between 0 and 1. All right, so this is how we do it. Is we say that the probability is equal to some function of our linear regression line. All right. Now this g function is going to be a cumulative distribution function. All right, it's going to be a cumulative distribution function. If that is when I say cumulative distribution function, if that's entirely if this is an entirely foreign concept, then come talk to me after class or do a little bit of research online, or maybe I'll try to do a follow-up to give a little bit more background on statistics to remind you what a cumulative distribution function is. I'll do a little bit of a reminder here, but it probably won't be thorough enough. And so if this is an entirely new concept, do a little bit more digging outside of this lecture. All right. So this g function is going to be a cumulative distribution function, and it will be either from a logistic distribution for the Logit model or a standard normal for the Probit model. I'll be more clear on that in just a moment. to do a mild review of what a cumulative distribution function is, a cumulative distribution function tells you the cumulative probability that a particular distribution of data will take on certain values. So what we have here is just as an illustration, we have a normal CDF. So that means we have a cumulative distribution function for a normal distribution. Okay, and what this tells us is it always goes from it increases from 0 to 1 on the y-axis, and then here are the possible values. And so what this is saying is that there's a very low probability, pretty much 0, very low probability, pretty much 0 probability of having a value of -4. And as you go up, this is kind of adding together the probability of experiencing different values. So there is some probability of experiencing a -3, and there's a greater probability in the data set for having -2 or below. And then there's a greater probability of having -1 and below. There's a greater probability of having 0 or below. There's a greater probability of having 2 or below. And eventually, all of your data, 100% of your data, is smaller than 4. So this is giving you the cumulative probability, the probability of finding any value less than the number given on the x-axis. So if you want to know what's the probability of getting a 0 or smaller, that's going to be right here around 50%. Actually, it should be right at 50%. Okay, so 50% of your data falls at 0 or below. 100% of your data falls at 4 or below. That's what this is telling you. All right, now we can see that a cumulative distribution function is bounded between 0 and 1. It's always greater than 0, and it's always less than 1. All right, so this is a perfect function to use here. If we want to make sure that the probability is greater than 0 and less than 1, then we can use a cumulative distribution function to constrain our values between 0 and 1. And so that's what we do. All right, so for a probit model, we are assuming a standard normal distribution. And for a logit model, we are assuming a logistic distribution. And then so here's the the functional form of those distributions. All right, and then I use as shorthand this x beta in bold here to indicate the linear function of the independent variables. Okay, so I'm not going to go into tremendous detail, although if you look in the book, if you look into the Introductory Econometrics, A Modern Approach by Jeffrey Wooldridge, you can find a little bit more detail in the appendix on how we estimate this. So when we use probit and logit models, instead of using ordinary least squares, we use what's called maximum likelihood. I'm not going to go into tremendous detail here, but basically we specify a log likelihood function. So it's the likelihood of observing different values, okay? And then we solve for the coefficients that give us the maximum likelihood that maximizes the log likelihood function. Okay, we can go through that more if you'd like, or you can find out more about maximum likelihood and solving maximum likelihood functions in the appendix to the textbook. All right, but now let's really get into what we're going to be focusing on in class. And that is when we use probit and logit models, what we are doing is we're using a different method. We're using this maximum likelihood method to estimate our coefficients. All right, so we're estimating our coefficients. But with probit and logit models, our coefficients are a little bit different. The way that we interpret them is going to be different than if we were using the linear probability model. All right, so let me explain. Whenever we run a model, what we want to know is we want to know how a change in the independent variable will affect the probability that y equals 1. We want to know, how does a change in the independent variables, how will a change in the independent variables affect the probability that the dependent variable equals 1. So therefore, we want to know basically, we want to know the derivative of the probability given, so the probability is a function of x, the probability that y will equal 1 is a function of x, given a change in the independent variable. That's what we want to know. That's what we want our coefficient to tell us. We want to know, how does a change in the independent variable affect the probability that y will equal 1? Okay, well, so when we use the probit and the logit models, what we're assuming is that the probability that the probability that the dependent variable will equal 1, that probability is now equal to some nonlinear function of our linear regression model. And so when we take the derivative, let's do that. We can take the derivative of the probability with respect to x1. That's what we want to know. We want to know, how does x1 affect, how does a change in x1 affect the probability that the dependent variable will be equal to 1? That's what we want to know. We take the derivative of this with respect to x1, and what we get is we use the chain rule. We get the derivative of g, we'll say lowercase g, so lowercase g is the derivative of capital G, all right, with this inside, all right, so the lowercase g is a function of this x beta times beta 1. Okay, watch my videos on derivatives to get a review of the chain rule to understand this derivative that we just did here. Okay, so what we see is that the change in the probability that the dependent variable equal 1 given a change in x1 equals beta 1, that's what we would expect, beta 1 times this other function. Now, if we took the derivative of just a linear function, let's say there was no g, if we took the derivative of just a linear function, we would get just beta 1. But when we're using a probit or a logit model, when we take the derivative, when we want to know the effect that x1 has on the probability of the dependent variable equaling 1, when we take that derivative, we find that it's beta 1 times some other function. Okay, now what does this mean? Why is that important? The reason that this is important is because beta 1, in a probit or a logit model, beta 1 hat, basically when we estimate this, beta 1 is actually not going to give us the marginal effect. Beta 1 doesn't give us how much the probability changes given a change in x. What we need is this whole expression. Beta 1 doesn't give us our marginal effect anymore. And that's what we want. We always want marginal effects. We want to know, how much does the probability change given a change in x. And so this presents a problem for us when we're using probit and logit models. All right, so this whole function is the marginal effect of a change in x1 on the probability. This whole function is. So that means when we run a probit or logit model in Stata, or in any other statistical software, when we run that model and we find beta 1 hat, beta 1 hat does not tell us what the effect that x1 has on the probability, because we need this whole function. We need this other term too. Okay, so we want to know how a change in the independent variables will affect the probability that y will equal 1. So what we want to know is this. We want to know the change in the probability given a change in x1. And we know that that will equal this. When we estimate beta 1 hat, we are not finding the marginal effect. When I say marginal effect, I mean this. A marginal effect is how a change in the independent variable will affect the probability. So that's what I mean by marginal effect. It's the effect on the margin. It's the effect of a 1 unit change in x1 on the probability. All right. So when we estimate a probit model and we find beta 1 hat, we're not finding the marginal effect. Because we don't just need beta 1 hat, we also need this function. So instead we need to calculate the marginal effects using beta 1 hat. How does that work? So this lowercase g of x beta, this is a function of the independent variables. So what we do is we plug the average value of the independent variables into x beta, and then we find the average of this function. So we estimate the marginal effects of x1, so we estimate it using this. So basically what we do is we take our estimated beta 0 hat, beta 0 hat plus beta 1 hat times the average value of x1. We plug that into this g function and then multiply it by beta 1 hat. And this whole expression will be our marginal effect. This whole expression will be the change in the probability that the dependent variable equals 1 given a 1 unit change in x1. Okay, we're actually not going to do this by hand instead, we're going to do it using the statistical software. We're going to just use a command for it, but I want you to know what's happening underneath the surface. We'll talk about it more, I'll explain it. Okay, so what we do to estimate the marginal effect is that we use the average value of the independent variables and our estimated values for coefficients. We plug that into this g function, we multiply it by our estimated beta 1 hat, and this will give us the marginal effect. So this is the predicted change in the probability that someone has a high school degree given a 1 unit change in x1. So we call this the marginal effect. So this whole thing is the marginal effect, and that's what we're interested in. We want to know the marginal effects. We want to know how a unit change in the independent variable will change the probability. All right. Now, let me compare these. So this is very important to compare this. All right, so this marginal effect is always what we want. We always want to know how does the probability change given a unit change in our independent variables. Now, if we use a linear probability model, so that means we have a dependent, we have a binary dependent variable, and we're using ordinary least squares. In that case, the probability is just a linear function. If we took the derivative of the probability with respect to x1, we just get beta 1 hat. All right, we get beta 1 hat, and I'm adding an extra subscript here, LPM, linear probability model. I'm adding that subscript just to differentiate it from this coefficient. All right, so this coefficient, this beta 1 hat, is going to be different from this beta 1 hat. All right, so if we use a linear probability model, all we have to do to know the marginal effect is to report the coefficient estimate. So all we need to know is beta 1 hat. Beta 1 hat is the marginal effect when we use a linear probability model. But if we use a probit model, all right, so now I'm focusing in on probit rather than logit because this is most common. If we use a probit model, if you remember, the probability that the dependent variable will be equal to 1 is equal not to just a linear function, but a nonlinear function of the linear function. Okay, so it's a nonlinear function. So when we take the derivative, we find, so the derivative, or the marginal effect, we want to know the marginal effect. The marginal effect is the derivative of the probability with respect to the independent variable. It's going to be beta 1 hat times this function, this lowercase g, the derivative of capital G, this lowercase g function of beta 0 hat plus beta 1 hat times the average value of the independent variable. Okay, so when we use a probit model, the marginal effect is not beta 1 hat, but instead it is this whole expression, which I'll show you how we deal with this in Stata in just a moment. Okay, so basically, when we're using different models, we need to remember what the marginal effect is and how we find it. All right, with a linear probability model, the marginal effect is just beta 1 hat. With a probit model, the marginal effect is this whole expression. And I'm going to show you in a moment how we calculate these using Stata. All right. Oftentimes, sometimes, but not always, these are similar to each other. Not always. They're somewhat similar. Okay. Now, I want to be more clear. Before I alluded to this issue of predicted values, I want to be more clear on these predicted values and their importance. Okay, predicted values. So we can use the coefficient estimates to generate predicted probabilities. So these are the predicted values of the dependent variable from either the linear probability model or the probit or logit model. Okay, so from a linear probability model, we can generate predicted probabilities. The predicted probability is just the yi hat. All right, every individual will have a different predicted probability. That's where we've estimated we've estimated beta 0, so we have beta 0 hat, we have beta 1 hat, okay, and we just solve this linear function and generate the predicted probability. We generate the predicted probability from the linear probability model. Okay, the predicted probability from the linear probability model is just the linear combination of our predicted beta 0 plus predicted beta 1, or our estimated beta 0 plus our estimated beta 1 times the independent variable. Okay, for a probit model, the predicted probability, we take our coefficient estimates, beta 0, beta 1 hat, so beta 0 hat, beta 1 hat. So we take the linear combination, plug that into the g function, and that will give us our predicted probability. So what I've alluded to before, is that with the linear probability model, this yi hat, this predicted probability, is not necessarily going to be between 0 and 1. In fact, sometimes it'll be less than 0, which doesn't make sense. You can't have a negative probability. And sometimes it'll be greater than 1, which again doesn't make sense. You can't have a probability greater than 1. Okay. But for the probit model, the predicted value, this yi hat, will always be between 0 and 1 because the g function is bounded between 0 and 1. The g function never goes below 0 or above 1. Okay, so that's what I mean by predicted values. We'll generate some predicted values when we look at Stata. Okay. All right, now I just want to talk a little bit about goodness of fit measures. So we're going to look at goodness of fit measures for the probit or the logit model real quick, and then we're going to go into our illustration. Oh, actually, no, then we're going to talk about when we use the different models. Okay, so one goodness of fit measure that we can use, goodness of fit, how well does the model fit the data? One goodness of fit measure that we can use when we're using, let's say, a probit model, is the percent correctly predicted. What we can do is we can generate a predicted dummy variable, which I'm going to call y tilde, or sometimes I'll call this y squiggle. It's kind of like a squiggly line, so I'll call it y squiggle or y squigs. That's what I've typically called it, y squigs. All right, so let this y squigs equal 1 or 0. Okay, so I'm creating a new dummy variable, y squigs. All right, and it equals 1 if the predicted value is greater than 50%, basically, greater than or equal to 50% or 0.5. You could have a different threshold here, but we're just going to assume 0.5. All right. And it equals 0 if the predicted value is less than 0.5. So basically, from the probit model, we've generated a whole bunch of predicted values. Those predicted values can be anywhere between 0 and 1. Those predicted values give you the probability that an individual has a dependent variable equal to 1. And we're saying, okay, let's cut it off at 50%. Basically, if you have 50% or more probability that your dependent variable will equal to 1, then we will set y squigs equal to 1 if you have more than 50% probability based on the regression model. If you have less than 50% probability, we'll say that y squigs equals 0. All right. And then what we do is we look at the percentage of the sample for which y squiggle equals y. That is the percentage of the observations for which the predicted value equals the data value. All right. And that percentage, so we'll say the percent correctly predicted. That means the percentage of the sample for which you have correctly predicted the dependent variable. That will be a measurement of goodness of fit. We'll take a look at that. All right, another one is when we use a probit model, we will use sometimes what's called the pseudo R-squared. So remember, R-squared is a measure of how well the model fits the data. It's always between 0 and 1. With a probit model, we can't calculate an R-squared in the same way that we would when we use an ordinary least squares, because when we calculate the probit model, we're not using ordinary least squares. We're using what's called maximum likelihood. We're using a different estimation strategy. So because of that, we can't calculate R-squared the same way. So instead, we do what's called a pseudo R-squared. The pseudo R-squared is 1 minus the log likelihood function for the estimated model, so L unrestricted, UR unrestricted, and divided by, all right, so the log likelihood function divided for the unrestricted model, that means your estimated model, divided by the log likelihood function for the model with only the intercept. Okay. We'll calculate this by hand in Stata in just a minute. Okay. All right, so now, okay, and just real quick, so this number is always going to be between 0 and 1. So it acts like an R-squared, where the closer it is to 1, the better, and the closer it is to 0, the worse. Okay. All right, now when to use which model? When do we use a linear probability model, and when do we use a probit model? All right, let's discuss the costs and the benefits of the two models. Okay, when do I use a linear probability model, and when do I use a probit model? All right, the advantages of the linear probability model is that they're easy to estimate and to interpret. The linear probability model, I'm just using ordinary least squares. So it's very easy to interpret. We can solve all of the problems using the methods that we have used so far in class. So for example, I can check for and solve for multicollinearity and heteroscedasticity with robust standard errors. So this is the most straightforward. Also, as I mentioned before, the marginal effects are just the coefficient estimates. So they're easier to interpret. All right, the disadvantages of the linear probability model are that the predicted probabilities can be illogical. That means the predicted probabilities can be greater than 1 or less than 0. Also, another disadvantage, although it's not a major disadvantage, the model's necessarily heteroscedastic. That means you know going in that it's going to have heteroscedasticity. But that's not a big problem for linear probability model because you can just use robust standard errors. Okay, so those are kind of the pros and the cons of the linear probability model. The pros and cons of the probit model. The pros are, the big pros, is that the predicted values are going to be between 0 and 1. That's a big advantage. The cons, I have one here. This is a major problem. I might add a second. I'll just verbally speak a second. I guess one con is that they're a little bit more difficult to interpret and estimate because you have to calculate the marginal effects in a different way, as I showed you before. But there's one big problem with probit models that is not often talked about. And we're going to talk about it more once we get into the Stata code, and I'm going to show you how to correct for it. But there's one major problem. Now, if you remember from lecture 7, you remember from lecture 7, I said that when we have heteroscedasticity, that causes our standard errors to be biased, but does not cause our coefficient estimates to be biased. Okay, so heteroscedasticity, when we're using ordinary least squares, when we're using a linear probability model, for example, is not a very serious problem. Heteroscedasticity, when we use a linear probability model estimated with ordinary least squares, does not cause bias in our coefficient estimates. They cause bias in the standard errors. But we can just use the robust standard errors and solve the problem. But when we use a probit model, heteroscedasticity actually causes our estimates to be biased, or what we would call inconsistent. Inconsistent means that they will be biased even if we have a large sample size. All right. Heteroscedasticity causes our estimates to be inconsistent. That means even if we have a big sample size, they're still going to be biased. Okay, that's a major problem. Heteroscedasticity actually causes our coefficients to be biased in a probit model. All right, that's a major problem. And there are some ways to solve it, but they're a little bit tricky. I'll show you in Stata. But basically, when we lay out these pros and these cons, we can kind of get an idea of when we should use one versus the other. And this maybe is my rule of thumb, and you might hear different things, because this is somewhat of a debated topic. But this is what I would say. If the reason I'm running my regression is to just get coefficient estimates, and I'm not concerned about generating predicted probabilities, then I would go with a linear probability model. If I'm running my regression and I need predicted probabilities, I need predicted values from my model, it's important that I have predicted probabilities, then I would go with the probit model, and I would try to solve the heteroscedasticity problem. But if I don't need predicted probabilities between 0 and 1, then I would probably go with the linear probability model, because solving heteroscedasticity in the probit model can be a little bit tricky, which I'll show you. I'll show you how to test for it and quote-unquote solve for it in Stata. But it's a little bit tricky to do so. And so I would probably favor the linear probability model unless I needed predicted values. Okay. All right, so now let's do an illustration in Stata. We're going to kind of illustrate the various things that we talked about during the lecture. All right, so what I'm going to do is I'm going to go and open up Stata here. Off to the sides, right? Okay, and then now I'm going to upload here. I'm using a data set. All right, let's just look at our variables. Here's a new data set. What I want to look at in this data set, what I'm asking myself, we're going to do some research on here, is we're going to look at what are the factors that determine whether or not an individual graduates with a university degree. So whether or not someone has a university degree. All right, we can certainly imagine why that would be important. Having a university degree really helps with lifelong income. And so we might want to know what are the factors that determine whether or not an individual has a university degree. All right, that's a binary variable. So this would be UD, university degree. It equals 1 if the individual has a university degree. It equals 0 if they do not have a university degree. And so now I am going to want to generate a model. I'm going to want to generate a model that will describe the factors that will communicate, I want to generate a model that will determine the factors that drive the probability that someone has a university degree or not. Now let's just confirm that this university degree is a binary variable. I'm just going to do tab UD, all right? So it is a binary variable. There's 505 total observations in my data set. 267 of them are 0. That means for 267 people don't have university degrees in my data set, and 238 people do have university degrees. All right, so here is a binary variable. It takes values of 0 and 1. All right, and so what we're going to want to do is we want to create a model that allows us to identify the variables, the determinants, the important determinants that determine the probability that someone will fall into one of these groups. What's the probability that someone will fall into what is the probability that someone will fall into the having a university degree group? What's the probability that someone will have a university degree? Now, to reinforce the point that I made at the beginning of the lecture, maybe we'll kind of go through this here. Just to reinforce the point that I made in the beginning of the lecture, the expected value of this binary variable is equal to the probability within the sample that someone will have a dependent variable equal to 1. So in this example, the probability that someone in our sample has a university degree, is going to be just the average in the data set. So let's just find what that average is. I'm going to do that again. Sum UD. All right. So the average, so the expected value of the university degree variable is 0.47. That means 47% of our sample has a has a university degree. 47% of our sample has a university degree. All right, that means there is a 47% probability that any individual in the data set has a university degree. And so now what we want to know is what are the factors that affect that probability? What are the factors that affect the probability that someone will have a university degree? That's kind of our purpose. That's what we're going to generate a model for. All right, so let's illustrate that. Let's do this. Lecture. Oops, I hit the lecture. This is lecture 9. And what are we doing in lecture 9? We're doing binary dependent variable models. All right. So now we mentioned before that we can do the linear probability model. 1, 2, 3, 4. And we can do, we're just going to focus on the probit model. That's much more common. Probit model. Okay. So I want to illustrate these two models. I want to talk about how to interpret them. I want to talk about the goodness of fit measures. I want to talk about the marginal effects issues. And I want to talk about, I want to reinforce for us when to use which model. And I think that's it. So let's go through that. So let's start with the linear probability model. So let's run a linear probability model first. Okay, so now when we're using a linear probability model, we're going to apply a lot of the things that we've already learned in class so far. So for example, when we build a model, again, what we do is we just, we use our theory and intuition about what we think the important variables are that will determine the probability that someone will have the university degree. That basically, what's the probability that the dependent variable will equal 1? All right, so we use the same intuition. So first of all, our dependent variable is UD, which is university degree. All right, and it's binary. It's a binary variable. And then let's think, what are the variables that are important? Well, let's look at the variables. We have their gender. We're not the individual's gender. Okay. We have married. Now, married equals 1 if their parents, if the student's parents are married. Income. This is annual income for the parents measured in $1,000 in units of $1,000. EDUC. This is the average years of education of the parents. So taking of the average of the years of education of the two parents. Job. This is the job sector that their parents work in. And GPA. This is the student's high school GPA. The GPA the student had in high school. So let's just think of a simple model. Let's say independent variables that we think are important. Let's say income is important, All right, if parents have a high level of income, they can afford to send their college to or their students to university. So income is going to be important. The education level of the parents will be important. I think GPA will be important. And let's stick to that. All right, so we're just going to do a simple model here. All right, so then let's do it. The linear probability model is the most straightforward. The linear probability is the most straightforward because all we're doing is the ordinary least squares. So we just do reg and then the dependent variable, which we know is binary, and then our independent variables that we think are relevant, GPA. All right, so then we just run that. Now when we do, okay, let's just run that first. Let's run that first and then I'm going to come back and run it again. We'll keep talking. All right, so I've just run my model. You notice we're using the reg command. This is ordinary least squares. Everything here should look familiar. Everything here should make sense because we've done this several times now. We have our r squared and our adjusted r squared as our goodness of fit measures. We have our dependent variable here, our independent variables here, our coefficients, standard errors, t-values, p-scores. We've got it all. All right, so this all looks very straightforward. Really, the thing that's different here that we need to focus on is how do we interpret the coefficients. Now, if you remember, and I'm just going to make a note over here to make it really clear, we want the marginal effects. All right, marginal effects marginal effects are the change in the probability, the change in the probability that the individual has a university university degree given a change in, what do we have, income or education of the parents or GPA. So what is the change? The marginal effect is the change in the probability that the individual has a university degree given a unit change in income, education, or GPA. All right, that's what we want to know. We want to know those marginal effects. All right, in a LPM model, linear probability, LPM, linear probability model. In an LPM model, the marginal effect is the coefficient estimate. All right, so if we want to know the marginal effect, we just come over here and we look at the coefficient. But now we interpret these coefficients differently. All right, so let's start with income and let's interpret this. What we're seeing here is that, so this is the marginal effect. So if the student's parents' income, if the income of the parents goes up by $1,000, that's a marginal increase. Remember, income is measured in units of $1,000. So if the parents' income goes up by $1,000, that will increase the probability that this individual will have a university degree by 0.6%. So whenever you're reading something in probabilities, you move the decimal place. You move the decimal 2 places. So the way that I would interpret this is that a $1,000 increase in parents' annual income increases the probability that a student will have a university degree by 0.6%. We can do it for education. For education, get a 1-year increase in the average education level of the parents results in a 1.5% increase in the student having a university degree. And then the GPA. A 1 point increase in the student's high school GPA implies an 18% increase in the probability that the student will have a university degree. Okay, that's how we would interpret these coefficients, holding all the other factors constant. So if parents' income goes up by $1,000, we would expect a 0.6% increase in the probability that the student will have a university degree, holding parents' education and GPA constant. Now, I mentioned that beta 0, remember the beta 0, I'm going to show, let's go back to that. I mentioned, let's see, beta 0 is the probability that the dependent variable equals 1 when all independent variables are 0. So what would that mean? This constant term, this gives you the probability that an individual will have a university degree if their GPA is 0, and their parents have no education, and their parents have no income. Now that's unrealistic. No one in the data set has no GPA, no education, or no income. But if that were the case, then the probability that they have a university degree is negative 90%. So this doesn't have a very clear intuitive interpretation, but that's what this is saying. This is saying that the probability that you will have a university degree if your GPA in high school was 0 and your parents have no years of education and your parents have 0 income is negative 90%. Okay. All right, so that's how we interpret these coefficients. That's how we interpret these coefficients. That what these do is these represent an increase in the probability that the individual will have a university degree given a unit change in the respective independent variable. Okay. So now let's talk a little bit more. So I mentioned in the lecture, that linear probability models will necessarily have heteroscedasticity. All right, but when we're using ordinary least squares, that's not a major problem. What we will do is we'll just use our robust standard errors. So let's just do that. We'll rerun the model, and now we're going to use robust standard errors. Okay, so now when we've done that, we have corrected. Now we have robust standard errors, so all of our coefficients are the same, but our p-values have changed a little bit, but actually qualitatively there's no difference. Income is still significant at the 1% level, education is still significant at the 5% level, GPA is still significant at the 1% level. Okay, so no major changes. No major changes here. All right, so we have to remember. So remember, when we use the LPM, we always need to report robust standard errors. All right. Now, let's talk a little bit about predicted values. All right, I mentioned before that the drawback, I'm going to take some notes here. The drawback for LPMs is that the predicted values don't necessarily fall between 0 and 1. That's the drawback. So let's do that. Let's generate some predicted values and take a look at what they look like. So when I say predicted values, that means what we're doing is we're generating the predicted probabilities that an individual will have a university degree or not. So what we do is we do predict. I'm just going to give it a name. We'll call it UD hat. All right, so this is going to be the predicted variable for the dependent variable. Okay, we're just going to do that. Predicted UD hat. All right. We're going to calculate this. Okay. And then let's open up our data set and take a look at what it looks like. So here is UD hat. All right, we've just predicted this. We used the coefficient estimates from our regression model, and we generated predicted values. You notice that all of these are in decimal form. These are all probabilities. So that means the predicted probability that person 1 will have a university degree is 23%. So the predicted probability that person 1 has a university degree is 23%. All right, the predicted probability, so now here we're going to have here we see the problem. The predicted probability that person 2 has a university degree is negative 18%. Well, it doesn't make sense to have a negative probability. So that's a problem. That's a problem for us if we want the predicted probabilities. If we think that these are useful and important and we need them for our analysis, then it doesn't make any sense. Okay, and we can keep going on. So the predicted probability that person 3 will have a university degree is 12%. The predicted probability that person 4 will have a university degree is 35%. The predicted probability that person 5 will have a university degree is 94%, and so on. We can keep going down the list. We can kind of get an idea for how good these estimates are. So these people, the first 3, none of them have university degrees. UD equals 0. And we can look at the predicted value and see they're all pretty low. They're all pretty small. In fact, one's even negative. These people all have university degrees. How well does this match? Well, these are all fairly large. This one's a little bit small. But these two are very large. In fact, this one's even greater than 1. So this person, the predicted probability that they have a university degree is there's a 114% chance that this person will have, that person 6 will have a university degree. Okay, so that illustrates our problem. We have we have predicted values that are greater than 1 and less than 0, which doesn't make sense for probabilities. We can even we can summarize our result, UD hat. We can find that the minimum value is negative, the maximum value is positive, and so we know that our predicted values don't make a lot of sense. Okay. And so this is a problem. This is a problem if we want those predicted probabilities. Sometimes in our analysis we want predicted probabilities. We need predicted probabilities. Sometimes we don't. If we need them, then the linear probability model is not the approach that we should use. Instead, we should use the probit model. Okay, so then let's now switch over to the probit model. All right, so now I mentioned in the lecture that the probit model is estimated using maximum likelihood. Okay, we're not going to go into the details on that, but what we're going to do is we're going to use Stata to estimate it using the Stata command. And the Stata command is just called probit. So it's pretty straightforward. We just use probit, UD, and now we're going to run the same model, GPA. All right, let's just run this first. Let me make some notes. Actually, no, I think we're good. We can carry it. We're using the same models we used before, so these notes still apply. Okay. So we're going to run this model. Let's take a look. So now we're running a probit model. The results are going to be a little bit different. Okay, when we run the probit model, we can see here that our output is a little bit different than before. So we can compare them. First, we have this log here, this iterations. This has to do with how the computer is solving the maximum likelihood function. It's different than how it solves for the ordinary least squares, but we don't need to, we're not going to focus on this right now. All right, it says probit regression instead of linear regression. So okay, here's an example of our results from the linear probability model. Here's an example of our result from the probit model, so we can compare them. So it says probit regression. It reports the log likelihood instead of let's just run this right next to it by comparison. We're going to get rid of the robust. We're just going to, so now we're going to compare them. We've got probit regression, and then here we have our linear regression. Under the probit regression, it reports the log likelihood value. We'll come back to this later. Here it reports the sum of squares, the different sum of squares. It's using a different method. Okay, you notice that when we use reg or when we use ordinary least squares, it reports the r squared and the adjusted r squared. When we use the probit model, it instead reports the pseudo r squared. We'll go back and calculate the pseudo r squared later. Okay, although you'll notice that the main bulk of it is pretty similar. We have the dependent variable, okay, just like that, dependent variable, independent variables, coefficient values, standard errors, t-values. Okay, now we're using a z-statistic, a little bit different, but the same idea. T-statistic, p-value, p-value. Okay, so these results, we can look at these and interpret these. We can read these results, the data output, in a very similar way. All right, so let me run this again, and we're just going to focus on this. All right, so here's our probit model results. Pseudo r squared, coefficients, standard errors, z-statistic, very similar to t-statistic, and our p-value. Okay, now, I might pause for a second and just make another quick note in here. Reg is the command for ordinary least squares. All right. And then I'm going to put here, probit uses the maximum likelihood estimation. All right, now, let's remember, in a probit model, so now we're going to talk about interpreting these results. In a probit model, the marginal effect is not the coefficient. Exclamation point. The marginal effect is that g function times the coefficient. All right, so now the question is, how do we get the marginal effects? What I'm saying here is that if I look at these coefficients, I can't interpret these. I cannot interpret these as marginal effects. I cannot say that as income goes up, the probability that that the person has a university degree goes up by 0.26. I can't say that. That's not how I would interpret these. These are not marginal effects. I want marginal effects. So what we need to do is we need to calculate them using these equations that I showed you in the lecture. The way that we get marginal effects using a probit model is that we have to plug in the estimated coefficients and the average variable values into this g function and then multiply that by the coefficient estimate. Okay, but we don't do that by hand. We do that using a command. So what we do is margins, comma, dy dx star post. This is the command. I put it after the probit model, and what it's going to do is it's going to report the marginal effects. You can kind of get a clue here. Dy dx, that's what the marginal effect is. The change in y given a change in x. The change in the probability given a change in x. All right, so that's what this is. Dy dx, the change in the probability given a change in x. And so what we do is we run this regression, and then we post the marginal effects. So what you'll see here when we run these two together is you'll see the probit regression output as we had before, and then below it you'll see what's called the average marginal effects. So now we're reporting the average marginal effects. Okay, and so now these values, these are our marginal effects. These are our marginal effects. You'll notice actually these are very similar to our linear probability model. Let me rerun our linear probability model just for comparison's sake. So here are our marginal effects from the Probit model, and here are our coefficient results, which are the same thing as the marginal effects for the linear probability model. You see they're very similar. Income is 0.006, this is 0.006. Education is 0.015, education is 0.014. Very, very similar results. So now, in the Probit model, I'm just going to rerun this. This is the most recent thing. This is what we would interpret as our marginal effects. And if I was to create a table, I would report these results, not these results. So if I was reporting a table, I would report these results, not these results. These are the marginal effects. These are what I'm interested in. So this is how I'd interpret this. I'd say that an increase of $1,000 in my parent's income, or in a student's parent's income, will increase the probability that the student will get a university degree by 0.6%. And an increase in 1 year of average income for a student's parents will increase the probability that they get a university degree by 1.4%. And an increase in GPA, in the student's high school GPA, by 1 point will increase the probability of getting a university degree by 17%. Okay, so that's what I would report here. These are the marginal effects. Okay, now let's look at the predicted value. All right, so now I mentioned before that the advantage of the Probit model is that the predicted values will be between 0 and 1. All right, so let's do that. Probit, UD, income, EDUC, GPA. All right, and we're going to do predict UD hat 2. All right, so UD hat 1, that was the predicted value from the linear probability model. Now we're going to do predict UD hat 2. This is going to be the predicted value from the Probit model. So we're going to compare them. So here we go. I generated it. Now let's open up our data set. Take a look. So here we go. UD hat, that is the predicted value from the linear probability model. And UD hat 2, this is the predicted value from the Probit model. Now, one thing that you'll notice is that in UD hat 2, it never drops below 0. So it can get really close to 0. So for example, this is 0.003, so that's basically 0.3% or 0.4%. And it get really high, so like here it's 0.996, so this is 99.6% chance. It's a very high probability of having a university degree here. But it never drops below 0, and it never goes above 1. And so this UD hat 2, the predicted value from the Probit model, is a more realistic and therefore probably more reliable prediction or generator of predicted probabilities. This is a more reliable predicted probability than the predicted probability that we get from the linear probability model. Okay, and we can summarize these results here. Let's do sum UD hat 2. Okay, the means are very similar, but we can see that for UD hat 2, the one that came from the Probit model, it doesn't drop below 0 and it doesn't go above 1. But for UD hat, it goes below 0 and above 1. Okay, so this is one of the major differences, and this is the advantage of the Probit model, is that the predicted probability is bounded between 0 and 1. Okay. So if I need to generate predicted probabilities for my analysis, then I will use the Probit model. If I don't need that, then I'll probably use the linear probability model. Okay, so now let's talk about this big disadvantage. The disadvantage of the Probit model is that the coefficient estimates are biased, or more technically speaking, inconsistent. Consistent. That means that even if I have a really big sample, they're still biased. Okay. When there is heteroscedasticity. All right. Now remember, heteroscedasticity is not a major problem for an ordinary least squares estimate because I can use the robust standard errors. But when I use the probit model, estimated using maximum likelihood, heteroscedasticity actually causes bias in the coefficient estimates themselves. This means that robust standard errors does not solve the problem. Okay. Now, heteroscedasticity is a big problem. So if I have heteroscedasticity, my estimates are actually going to be biased or inconsistent. That's a big issue. We need to be able to test for that. We need to be able to test whether or not there's heteroscedasticity, and we need to be able to control for it. Now, there is a command in Stata that we can use to test for or control for heteroscedasticity. But before I use it, I just want to say that practically speaking, if I think that there's going to be a serious heteroscedasticity problem in my probit model, then I'm probably going to use the linear probability model to avoid that the bias that can be introduced from the heteroscedasticity. But I want to illustrate to you how we can test for it and solve for it. And actually we do it in one fell swoop. Testing and solving. All right, I'm not going to go through all the details here on how this works, but we're going to use a command called hecprobe. Hecprobe, what we're going to do is we're going to include our model here, comma, het, and what this code is doing is I'm going to run the regression model, and I'm going to correct for whatever variable is causing the heteroscedasticity. So you can include all of your independent variables in here, or you can include just the variables that you think are the variables that are causing the heteroscedasticity. For right now, I'm just going to include all of them, and then I'm going to run this. And what this does is it gives me the regression results, and it performs a test to determine whether or not there is heteroscedasticity. All I'm going to focus on is this down here. So this is a p-value for a hypothesis test. It's testing the null hypothesis that there is no heteroscedasticity. And so if I reject it, that means I'm saying that there is heteroscedasticity, or I have evidence to suggest that there's heteroscedasticity. And so if I look at this, I can see that this is significant at the 5% level, which means that I can conclude that there is heteroscedasticity. And then this reports my coefficient results that are robust to that heteroscedasticity. But now I don't want the coefficient results, I want the marginal effects, so I come back in and say margins dy dx, comma star post. And so now I'm going to calculate my marginal effects, and now these will be my heteroscedasticity robust estimates of the marginal effects for my probit model. Okay, so this would be testing and solving for the heteroscedasticity. All right, I haven't gone into the details of how this works, but I think it's a little bit beyond the scope of certainly this lecture and probably this class. So this is the way that we would solve for it. But this is a little bit more technically complicated, and unless you have to use a probit model, I would go with the linear probability model. So if I don't need the predicted values, for my analysis, what I would probably do is I would probably run this het_probit model here. I'd run this model, and then I would see, do I have heteroscedasticity? I'd look at this, I'd say, okay, yes, the evidence suggests that I do have heteroscedasticity. So I would then just switch back to the linear probability model and use robust standard errors, and I would just use this result. That's how I would probably proceed here. If I need the predicted values, then I'd come back and I'd use this one. Okay. Now, last thing that I'm going to go over is the goodness of fit measures. All right. So I mentioned two new goodness of fit measures. One is the percent correct predicted. So the percentage of the values that was correctly predicted by the regression. We can use this for the linear probability model or the probit model, either one. Let's do it for the probit model. So what I'm going to do is I'm going to take my probit model. I'm just going to show you this by hand. All right. Okay. So we're going to run a probit model. All right. And then what we're going to do is we're going to predict. I'm just doing it again. I've already done it. UD hat 2. All right. I'm just going to real quick. All right. So I'm going to run the probit model and I'm going to generate the predicted probability. Now what I'm going to do is I'm going to generate a new variable. All right, generate, remember my y squiggle. So UD squiggle. All right, UD squiggle. All right, just remind you what I'm doing here. Let's go back to the lecture. What I'm doing is I'm doing a goodness of fit measurement of percent correctly predicted. I'm generating a new variable. It equals 1 if the predicted value is greater than 50% and 0 if the predicted value is less than 50%. And then we're going to look at the percentage of the sample for which this new predicted value, this y squiggle, is equal to the true value, the value in the data. So now I'm creating this y squiggle. All right, it's going to be a dummy variable, and it's going to equal 1 if u hat 2 is greater than or equal to 0.5, and it'll equal 0 otherwise. So now I'm going to do that, create this. Now, I'm going to create another variable. I'm going to generate a variable. I'm going to call it, let's see, I'm going to call it correct prediction. All right, long variable name. It's going to equal 0. Let's see. Let's do it a different way. All right, it's going to equal 1 if UD squig. That should be a G. Squig. UD. Oh. Drop UD. Sorry. All right, here we go. All right, it's going to equal 1 if UD squig equals 1 and UD equals 1. So this is going to be a variable that it's a dummy variable, equal 1 if our prediction correctly predicts the outcome. Okay? So it correctly predicts if UD squiggle equals 1 and UD equals 1. That would be a correct prediction. It will equal 0 otherwise. All right, so let's generate that. Now I want to know what is the percentage of the sample that has correct prediction. So the percent correct predicted. What is the percent of the sample that has a correct prediction? Of course, the higher the better. All we need to do here is generate the expected value, right? So the expected value of correct prediction equals the percent of the sample that has a correct prediction. So let's just do sum correct prediction, and the higher this number is, the better. The higher this average is, the better. All right, correct prediction, 36%. Only 36% of the sample has a correct prediction. Actually, let's see. No, I'm sorry, I need to correct this. Correct prediction should equal 1 if both of these equal 1, or, okay, sorry about that, or if both of these equal 0. Yeah, that's it. All right. Something was wrong there. All right. It's if both of them equal 1 or both of them equal 0. That means that when UD squigs equals 1, UD equals 1. That'd be a correct prediction. If UD squigs equals 0 and UD equals 0, that's also a correct prediction. It's an incorrect prediction when UD squigs equals 1 and UD equals 0, or if UD squigs equals 0 but UD equals 1. Those would be incorrect predictions. All right, so now I need to drop correct prediction. Drop that. Regenerate it. Here we go. So these are ands, and then this is an or symbol. All right, let's do this again. There we go. This will give us much better. All right, 80%. 80% is pretty good. Basically, we're saying that 80% of our predicted values predict the correct value in the data set. 80%, that's pretty good. That's not bad. That's a pretty good predicted value. We could repeat this all for the linear probability model and compare them. Let's do that for fun. All right, reg. All right, we're just going to repeat for the LPM, linear probability model. All right, I'm just going to call this y hat 3. All right, I'm going to call this squig 2. 3. Actually, I'm going to change this. LPM. There we go. LPM. LPM. Okay. LPM. LPM. Correct prediction, LPM. And then LPM. All right, so now we're competing with 80%. So which one is going to do a better job of generating a predicted value? Let's see. Okay, they're both pretty much 80%. This is 80.6% and this is 80.4%. They're pretty much the same. Okay, so that's one measure of goodness of fit. The higher this percentage is, the better that it fits the data. All right, the other one is the pseudo R squared. All right, now this is used with the Probit model. Now, if you remember, the pseudo R squared is 1 minus L unrestricted divided by L naught. All right, well, let's clarify what we mean by that. All right, so what we do is a Probit model, and then we would do a Probit model with just, so the unrestricted model is the Probit model with all the independent variables. So that would be this one. LUR is this value here. All right, so we can start plugging this in. 1 minus negative 211.9. All right, divided by, and then we'll do the Probit with only the intercept term. All right, negative 349.2. All right, now let's calculate this. Let's get the calculator out. All right, 211.9 divided by 349.2. All right, so that is 0.607. All right, and then it's 1 minus that. 1 minus 0.607. So that equals 0.393. So now let's check that. That should be our pseudo R squared for our regression, 0.393. So our pseudo R squared is 0.393. That's exactly what we calculate. That's how you calculate it. That's the pseudo R squared for the for the probit model. Okay, so there we go. There's our regression on binary dependent variable models, and I hope that you enjoyed the lecture, and please review this code thoroughly, follow along with the lecture, and be prepared to implement some of these things in class. And with that, I hope you have an excellent day. All right, bye.